Good morning and good afternoon to you all. Today we have the defense of the PhD thesis of Galina Chikunova on the coronal dimmings associated with coronal mass ejections, evolution, lifetime, and relation to the directivity. So before we start, I would like to give a brief reminder of the PhD defense procedure. First, we start with the introduction of the jury members and the candidate. Next, the candidate's presentation, which is up to 40 minutes. This will be followed by questions and answers. First, questions from the jury. And please, jury members, each jury member must confirm whether they are satisfied or not with the changes introduced to the thesis after their review. Then questions will be extended to general audience in Zoom and also here, if anyone in the audience would like to ask scientific questions related to the doctoral work. After that, we will have the word of the supervisor and the closed deliberation. So for the jury members who are online, there will be a Zoom breakout room. And we will be discussing the defense, the questions and answers, and we will be voting to decide about the defense outcome. And after which we will announce the outcome of our decisions to the candidate. Well, now I turn to the introduction to the jury members and the candidate. We have with us today Dr. Vladimir Kalegayev, who is head of the Department of the Space Sciences at Skobeltsyn Institute of Nuclear Physics of the Moscow State University. Since joining this institute, Dr. Vladimir Kalegayev has been actively engaged in scientific research on solar terrestrial connections, Earth's magnetosphere, radiation belts, magnetospheres of planets in the solar system, space weather, and more. Under his leadership, a space weather monitoring center has been created at the Skobeltsyn Institute of Nuclear Physics. Dr. Kalegayev is part of a team and who was awarded the first degree Lomonosov Prize in 2011 for the series of work entitled Magnetospheres of the Planets in the Solar System. Dr. Kalegayev is a member of the Scientific Council of Moscow State University, a corresponding member of the Space Council of the Russian Academy of Science. Next. We have with us Dr. Anatoly Petrukovich, who is director of the Space Research Institute of the Russian Academy of Sciences. He graduated from the Moscow Institute of Physics and Technology, MIPT, and received a PhD degree in 1994 and Doctor of Science degree in 2003. Since 2011, Dr. Petrukovich is a corresponding member of the Russian Academy of Science. His main research interests are in the dynamics of Earth's magnetosphere and space weather. He is actively involved in teaching at MIPT and at the Higher School of Economics, HSC. During the 90s, he took part in the Russian and international space projects Interball, Geotail, cluster. He's involved in the management of the development and conducting experiments on the Russian spacecraft, Spectre-R, Resonance, and Luna Globe. Dr. Petrukovich was an associate editor of the Journal of Geophysical Research, Space Physics section, between 2012 and 2014. And he's now editor-in-chief of the Russian Cosmic Research Journal. He's the head of the magnetospheric section in Solar Terrestrial Council of the Russian Academy of Science and head of the Solar Terrestrial section. Yes, and repeated twice. Good. We have here with us Dr. Hugh Hudson, who is a honorary research fellow in the School of Physics and Astronomy at the University of Glasgow. His main research interests are in high-energy solar physics, solar X-rays, solar flares, and coronal mass ejections. But he also carried out research and published on all aspects of solar physics. He has been associated with several space-based solar observatories, in particular YOCO and RECI. His most recent research topics have included the investigation of the phenomena associated with a recent unusual solar activity cycle and the observation and interpretation of highly energetic phenomena in the solar atmosphere. Next, Dr. Stefan Hofmeister is an associate research scientist at Columbia University in the US. Dr. Hofmeister graduated with a PhD in astrophysics at the University of Graz in Austria in 2019. He received the PhD thesis prize of the European Solar Physics Division of the European Physical Society and the Award of Excellence of the Ministry of Science of Austria in 2020. His primary research focus is on the solar-terrestrial relationships, how structures on the sun shape the interplanetary space in our solar system, and how they affect the Earth's environment. Here at Skoltech, we have Professor Clément Fortin with us. So he's Dean of Education and full professor at Skoltech. He joined Skoltech in 2014. Between 2010 and 2014, Professor Fortin was president and CEO of the Consortium for Research and Innovation in Aerospace in Quebec. He had previously been the director of the Department of Mechanical Engineering at École Polytechnique de Montréal and a professor at this institution since 1987. Dr. Fortin created Polyplan Technologies, a spin-off company of École Polytechnique. The company developed an innovative product lifecycle management solution for concurrent engineering. Professor Fortin is a fellow of the Canadian Academy of Engineering. My name is Anywhere Dan. Today I'm the jury chair. I am an associate professor at the Skoltech Center for Digital Engineering. I earned my PhD at Heriot-Watt University in Edinburgh, Scotland in 2002. Since then, I've been actively involved in, and I have also led various projects in physics and engineering. And more recently, I earned a master's degree in European project management from the University of Caen in France. I joined Skoltech as a leading research scientist in 2017 to work on the project Integration and Control of Heat and Power Systems with Variable Loads. It was funded by the Next Generation Skoltech MIT program. And currently, I'm developing my research activity at Skoltech with a consideration of use, principally working on energy conversion physics and systems modeling. I currently serve as the director of the Skoltech Engineering Systems PhD program and chair of the Skoltech Educational Committee. Our candidate supervisor is Professor Tatiana Podlachikova, who is associate professor and the director of the Skoltech Center for Digital Engineering. She joined Skoltech in 2013, working previously in the Royal Observatory of Belgium, Laboratory of Astrophysics in Marseille, and Space Research Institute of the Russian Academy of Sciences. Her scientific interests are related to solar and solar terrestrial physics and space weather. She developed a number of space weather services, including sunspot number, solar radio flux, and geomagnetic storm forecasting, prediction of arrival of high-speed solar wind stream towards Earth. Dr. Podlachikova is the coordinator of the Skoltech Master Program Engineering Systems. She holds numerous awards, including the International Alexander Shijevsky Medal for Space Weather and Space Climate 2015 in Belgium. She has been receiving also other awards like Best Professor of the Year 2018 for mentoring, Best Professor of the Year 2019 for lecturing, and Best Professor of the Year 2020 for teaching excellence at Skoltech. She got recognition for excellence in research, teaching, impact, and service to Skoltech and the wider community in 2022 and 2023. Our PhD candidate is Galina Chikunova. She earned her BSc degree in applied physics and math from Moscow Institute of Physics and Technology, MIPT, in 2017. She completed her master's program in information systems and technologies at Skoltech, working with Dr. Tatiana Podlachikova and undertaking an academic mobility trip to the University of Graz in Austria. Throughout her PhD studies at Skoltech, her research focused on studying coronal dimmings associated with eruptive events on the sun. Since 2020, as a young scientist, she participated in a series of international team workshops organized by the International Space Science Institute in Bern, coronal dimmings and their relevance to physics of solar and stellar coronal mass ejections. She presented her results at a number of international conferences and summer schools. At Skoltech, Galina served as a teaching assistant for the courses Experimental Data Processing and Data Analysis for Space Weather. She's also initiated the ISP individual study period winter course, Solar Observations with a Telescope for master students. Now, it's time for the candidate's presentation. So, Galina, you may start when you're ready, and you have up to 40 minutes.
Thank you so much. Good afternoon, everyone. Thank you for coming today. My name is Galina Chikunova, and today I will present you my PhD thesis called Coronal Dimmings associated with coronal mass ejections, evolution, lifetime, and relation to the directivity. My research lies in the area of space weather. Our sun is not only essential for life on Earth, but also can create very disruptive forces, the most disruptive that our planet can face. And if active eruptive events from the sun is Earth directed, it can hit our magnetosphere and create a geomagnetic storm, which causes a lot of space weather effects. Among these effects are high radiation doses for our astronauts on ISS and for our future missions to space. On Earth, it's also high radiation doses for airplane crews, damage for electronics, disruption of navigation systems, communication. Also, its induced currents can damage power station on Earth and other effects. So let's have some attention on historical events. I mentioned some events for each century, but of course there are more and more events which were related to space weather. The most classical event is Carrington event, which happened in 19th century. And this is the most known, the strongest solar flare. And that time there was so huge geomagnetic storm that the polar aurora were across all the globe and could be seen also on the equator. And telegraph system, the only one actually communication system that people used at the time, went out of order everywhere. If such event would be carried nowadays, with our technologies, it could cost us much more money and much larger disruptions of our system. Another event which I want to mention happened in 20th century, and it's Quebec blackout. At that time, the magnetic storm hit out electricity, and in winter, a lot of people in Canada were for hours without electricity, heat, and in condition of panic and not understanding what's happening. Reports suggest the loss up to $13 million for economy of Canada. The last event happened which I want to mention, the last event which happened last year, and SpaceX Starlink satellites didn't make it to orbit, and they burned out in the lower atmosphere and didn't reach the orbit which was planned. And at that time, the storm was not too strong. It was moderate, but still it costed a lot of money for company due to no opportunity for a reliable forecast for that time, because the event was complex and nobody expected such conditions. So all of these events are made because of the solar storms and eruptive events happening on the sun. And nowadays, society more and more concerned about space weather, and Space Weather Prediction Center in US reported a rapid growth of subscriptions for their services for reliable forecasts. And this plot is interesting that it shows the rapid growth of user numbers for space weather services through years. And also it shows the solar cycle. So for the last 2 solar cycles, people are more and more interested in space weather services. So the causes, one of the main drivers of space weather effects are coronal mass ejections, eruptive events on the sun. And these are huge clouds of magnetized plasma that are expelled from the sun to space and carry out billions of tons of matter with very high speeds. It is very important to understand the nature of this phenomena and try to make reliable modeling to forecast the consequences, but it's very hard to do. Coronal mass ejections are seen happening in coronal atmosphere, which is less dense than solar disk. And that's why scientists use coronagraphs to study coronal mass ejections, but now we have only 2 coronagraphs in space. And it's very hard to estimate the parameters of coronal mass ejection for reliable modeling. We have serious projection effects, lack of instruments, and we block all the early evolution of the event with using coronagraph. Usually scientists define 3-part structure of coronal mass ejections because it's a magnetic structure. It consists of bright core, which is usually filament, cavity, which is less dense and dark, and a bright loop. But also it's very hard to resolve such structures due to lack of instruments. And that's why we need also to define some other methods how to define the parameters of coronal mass ejections. And another way could be to study associated phenomena. And the most distinct phenomena related to coronal mass ejections are coronal dimmings. These are regions of strongly reduced emission in soft X-rays and extreme ultraviolet. And they're happening together with coronal mass ejections caused by evacuation of plasma. We can define them as a drop of UV intensity. And we usually describe double nature of coronal dimmings. So there are core dimmings. I can try to show, if you will see my pointer. Yeah. Core dimmings, which are more localized region, and they map the foot points of the flux slope of coronal mass ejection, and more diffuse secondary dimmings, which show the expansion of overlying magnetic field. And you can see them also in the observations of UV corona, core and secondary. The coronal dimmings are interpreted as a density depletion due to evacuation of plasma, and they're related with the mass loss during the semi-eruption. And this is confirmed by a number of studies, by observations in different wavelengths, by estimating the outflow within dimming regions. Also, the temperature effect is not so drastic as the density drop within these regions, and also in spectroscopy. We can detect coronal dimmings on disk on the sun, as you can see here, and also check them off-limb from different viewpoints. And that's what we do in our research. Let's start with our research objectives. In our research, we want to show how can we use information on coronal dimmings to estimate the properties of coronal mass ejections. Nowadays, despite of a number of papers and research on this topic, still we have lack of understanding of the connection between two phenomena, and we need more deep work and more statistical analysis. So I divide my work into 3 parts. The first question, which will answer how can we use dimmings to estimate the mass and speed of coronal mass ejection, then how and when the solar corona recover, how long we can detect coronal dimmings after the semi-eruption, and how the early evolution and morphology of dimmings connected to the propagation direction, also of coronal mass ejection, also very important parameter for modeling of coronal mass ejection. So we'll study the relationship between these two phenomena and develop the framework for their analysis. We'll highlight the unique potential of coronal dimmings, not only to indicate eruptions on the sun, but also to define and estimate their parameters on the very early stages, even before we can detect them by other instruments. My research, we already published in a number of publications, which I show you here. And also this work was supported by a Russian Science Foundation grant. Let's start with the first question, in relation to coronal mass ejection mass and speed. The first and the latest, most comprehensive analysis of coronal dimmings was done by our colleagues from University of Graz, by Karen Dezauer, in a number of papers. And here they discuss a set of events which happened between May 2010 and September 2012. This is a list of 77 events of, where coronal mass ejections were directed to Earth and were seen during quasi-quadrature of SDO satellite and stereo satellites. So coronal dimmings were detected on disk, and the parameters coronal mass ejections were measured without significant projection effects using stereo satellites. And this analysis proves high correlation coefficient between parameters of coronal dimmings and the mass and speed of coronal mass ejection. And my task was to use the same list of events, but study coronal dimmings not on disk, but off limb using both stereo satellites that you can see here, how the dimming looks like off limb. So finally, my number of events was 43 events. We used time cadence of 5 minutes of UV data, and we tracked coronal dimmings for 12 hours. For this project and for all other projects, we developed a comprehensive framework for the dimming analysis. And in this work, we define procedures for loading, calibration, data, and differential rotation using Python. And we translated different routines from ideal solar soft, which traditionally used. And nowadays, Python library SunPy develops rapidly, but still not a lot of, not all functions open source for society. And for example, we can't make proper calibration of stereo data. So we use both ideal and Python for calibration and differential rotation. Differential rotation should be done to construct and pre-process images for coronal dimmings. I will describe it also a bit later. Next, we also define an area correction method. So we define morphology of dimmings, and it's important to accurately estimate the area, but the sun is not 2D. We define the area correction in 3D space on the solar surface, and I will show also how to do it. We define the methods of preprocessing data, and coronal dimmings show only small changes of intensity, and that's why we need to construct base difference and logarithmic base ratio data. For that, we need to proceed differential rotation of all images in the set to the pre-event image. And then we need to define, to subtract intensity of base image from the set to create base difference data, and not subtract, but create ratio of intensity for logarithmic base ratio data. And I show here how the dimming looks in original data. It's hard to detect it here, but in processed logarithmic base ratio, we can see the dark region. So next, we develop automatic dimming segmentation approach. And I will show you our approach for off-limb observations. And for on-disk, we use the method introduced in the work of Karen Dezauer, but we also translated to Python language from IDEO. Then we define how to extract and describe the characteristic dimming parameters and how to relate these parameters to parameters of coronal mass ejections. So let's describe the dimming detection algorithm. Usually dimmings are detected in base differences. I already mentioned all logarithmic base ratio, but for off-limb detection, it's impossible to use only one type of data. We prefer to use logarithmic base ratio data because for off-limb, the parts of coronal dimmings can be detected in higher layers of atmosphere with less density. And for that regions, we need to equally consider the intensity of pixels from the low corona and from the upper. Not from the low corona and the upper, but like lower regions and more higher regions. And we define the thresholding for this type of data. We empirically check intensity level of images for different events. The histogram on the left shows 2 events. The black one shows intensity distribution of pixels before the event, and green shift during the extension of the dimming. So we can see that the dimming, the pixels shift to the negative, and we can define the dimming region within these pixels. Empirically, we define the level of minus 0.19, which in linear space refers to drop of intensity of 35%. Then the problem of logarithmic base ratio data for off-limb is that we have a lot of noise in the higher layers of corona because of equally considering the pixels. And what we do, we use region growing algorithm, but define the seed pixels which will be connected not in the same data, but we use base difference data, which doesn't have this noise. So we define soft thresholding level for base difference data and grow these pixels, which are green here, in the base ratio data. And only the pixels that have neighbors will grow. And that we have nice detection of the dimming. We also can apply median filtering or label region function to more accurately define these detections. And we do this for every image in our set, and this allows us to track the dimming evolution and make instantaneous parameters at every time step, and also cumulative, which integrate all the pixels which were detected up to every moment, which I show here. So together with associated work, these 2 projects are the first multi-viewpoint analysis of coronal dimmings and coronal mass ejections. And here I show you the example of one event, how it looks like for on-disk and off-limb viewpoint. For SDO data, stereo, logarithmic base ratio, and so-called timing maps, which we use to describe the dimming morphology, and we color code the time when the dimming pixel was detected for the first time. Such analysis is very important for missions at L1 and L5 configurations, which observe coronal dimmings and coronal mass ejections on disk and off-limb respectively. So we track the evolution of dimming parameters and define the metrics for our statistics. Here I show you cumulative and instantaneous area and brightness. We also define the dimming impulsive phase, the time of rapid growth of the dimming, and we define it as the first local maximum, minimum, and the time when area derivative drops by on the 15%. And I show the impulsive phase as vertical lines. Within the impulsive phase, we define the maximum area and the minimum for brightness for statistics. And we also check the change rates for these metrics. Here I show you the statistics, the distribution of these values, and the mean and parameters. So then we can refer these parameters, this dimming characteristic, to parameters of coronal mass ejections. And I will describe the most important outcomes of this research. We confirmed the relation between coronal dimming and coronal mass ejection also for off-limb viewpoint. Dimming area and brightness strongly correlate with the masses coronal mass ejection as for on disk. And you can see these plots of dimming area and semi-mass relation. And for off-limb, we have even higher correlation coefficients because the parameters of coronal mass ejection were defined from the same viewpoint. So it's also important to check the off-limb dimmings. The change rates of dimming parameters correlate with the speed of coronal mass ejection. We compared also dimmings characteristic between off-limb and non-disc, and we defined the dimming areas typically larger, but with lower intensity. That means that there is a lot of contribution of higher layers of corona to the dimming region. So this work proves the high potential of the dimming observations to provide us early estimates of the mass and speed of coronal mass ejections on the very early stages. Next question, dimming recovery time. This is also very unclear question, and it's very important to thoughtfully describe the research question and how to define the metrics to answer it. In addition to parameters which we defined in the statistical analysis, we also tracked the recovery time. We defined the metric for this as the time between the maximum area of the dimming to the time when it drops by 50%. And we, as we checked the dimmings only in 12 hours, a lot of recovery times were underestimated in this analysis, but we could already see some distribution. Our distribution of recovery time shows that indicates that can be two classes of recovery of dimmings, fast and slow, which also was reported in a number of studies. And it can indicate that there are two possible classes of recovery. So dimming can show signatures of the flux rope, which prevents the recovery. And here we have slow recovery, more hours. And the fast recovery, when dimmings only indicates expansion of overlying corona, recovers fast within 6 hours. For making more conclusions, we need more to track dimming in more detail and for larger time evolution. We also can compare the mean value, which we find of 5.6 hours to related works, but we also need to be careful because different works define the time recovery in different ways, and the dimmings that they detect also differently. For example, in the last work, only core dimmings were detected, so the time can be different. So to proceed with the method to define the time recovery of dimming, I will show you 4 case events of different complexity of events with different flares. 3 of events will happened in the solar maximum and 1 in the solar minimum. We also have 1 event, June 2012, associated with long durated flare. And we will introduce the methods showing on these events. The most important limitation to study the recovery of coronal dimmings is the fact that we need to correct the images for the differential rotation. As the sun is not solid body, the equator rotates faster than the poles, and that's why we need to correct the images. And when we detect the dimmings, we need to have one base event, base image, and then rotate all other images to this image. And as we track for 3 days, you can see the difference in the image after correction for 3 days. So we have a lot of artifacts of differential rotation. And as dimmings describes, but it's morphology, these artifacts can significantly affect our results. That's why we need to come up with methods that eliminate these artifacts. We introduce a fixed mass approach. Here I show you the event 7 March 2012. You can see on the video original data, base difference, and logarithm base ratio, which we already calibrated, rotated. And if we just detect the dimmings and define its instantaneous masks, as I can show with red color in here, we will detect a lot of rotation artifacts, which exploits our data. We track the dimmings both on disk and off limb, and I show on this plot the evolution of area instantaneous, red for off limb stereo data and blue for SDO. We show brightness and we show the associated flare flux. What we can see is rapid growth of area and rapid decrease of intensity. And then for on disk, we always have increase of area and decrease of brightness. But for stereo data, we see that the increase stops at some point, and then it grows only when second event happens. If we check the images, we can see that actually our detection was significantly spoiled by these artifacts. And what we can do with it, we define the fixed mask, and we track the dimming parameters only within fixed mask. This fixed mask is a maximum instantaneous mask within the impulsive phase of the dimming. And I can show it here with the blue region. So we track the intensity in the area only within fixed mask. And in the last panel, I show the intensity within this. And we can see that actually intensity shows the recovery of this region. We define the parameters within fixed mask for all these 4 events. And here we can compare them. The left panel shows brightness and the right is area. And we can see that 3 or 4 events actually perform recovery within 1 day. So all these panels show 1 day of tracking. Only one event, 7 March 2012, doesn't show recovery. So it's still here. Also, we can see that 2 events show firstly rapid growth of intensity because of flare pixels also introduced into mask for dimming, other events not. We also can compare the dimming recovery with the flare impulsive phase and duration. About flare information, we show it with gray color. So we can see that there is one long durated flare, but still shows recovery. We also can see that our drop, so we have drop of intensity and recovery we check after this minimum. And you can see that for example, for September, we have 2-step recovery. Firstly, it's very sharp and then it's more steady. And for other events, we also can see indication of this behavior, which was also reported in associated work. So our method can reliably allow us to track the dimming, the recovery of dimming intensity and area. But here we check only the total dimming mask, and very important also to check core and secondary dimmings separately. And we need to develop another method to allow us to do that. And we introduce a fixed area box approach. We define squares, 3 by 3 pixels, and we tracked dimming intensity within these squares. So we can locate the square in region of interest to core dimming, to secondary dimming, maybe to check twin core dimmings of different polarities, depending on the question which we want to answer here. Here I show event 8 March 2019 and different location of the box. And you can see their different behavior. And gray box shows non-dimming part, quiet corona, which just distributed around 0. And we show original intensity and logarithmic base ratio brightness. So we can see that different parts of the dimming actually recover very differently. And we should be aware of that. Also for this event, for March event, we for the total fixed mask, we saw total recovery, but you can see that, for example, for this part, for Rose region, we don't have full recovery. So this is also important to consider when we analyze recovery of the coronal dimmings. So we already see how that methods has a potential to investigate different parts of the dimming and that some parts not recover up to 3 days. I also want to show you case studies, which also introduce the potential of dimming to show us another other parameters, coronal mass ejection, other information which I didn't mention. And it's important to study dimmings together with other signatures of the coronal mass ejections. So these are not the only phenomena which goes in association with coronal mass ejections. And the first study, which was published, it's International Women's Day event. And this is the study from Sun to Earth, where all the signatures were studied. And my task was to study coronal dimmings. And this is 8 March event, which I showed before. And here I can show you the video of this event and the detection mask of the dimming. The interesting fact about the study is that in coronagraphs, we could see only one event, one entity, but all the other signatures in low corona indicated that there is something happening twice. So there are 2 events, or it's a double eruption of the structure. When we track coronal dimming, we can see that, maybe I can make it another time, that actually its evolution goes firstly to one direction and then to another. When we track flare, we can also see double peaks for this event. And actually they are in the time correspondence with the peaks in dimming evolution. What I introduce here is our framework allows to just divide this dimming into 2 parts and track them separately, what I'm showing here on the plot. Here I show you only 1 hour of the dimming evolution during its impulsive phase, and we can see how differently the 2 parts of dimming evolve. For this event, we also have double peak flare, double evolution of dimmings, and also 2 coronal UV waves, and that all means that our low structure of coronal mass ejection indicates of complex structure of the event, but coronagraphs didn't resolve it. That's also very important to consider. So dimming observations can provide information about the complex structure of event, which is very important for accurate modeling results. The next study, also case study from Sun to Earth, 2nd November 2021. And here we checked, as a task for the, as a part of the study, we checked the magnetic flux within the dimming regions and flare ribbons. For that, we use HMI maps, HMI magnetograms, which I show here. You can see regions of opposite polarity. We check photospheric region for detection of flare ribbons, and also 2011 for detection of coronal dimmings. Usually, flare ribbons are used to define the magnetic flux, which released during flare, but also coronal dimmings together with flare ribbons can be a very reliable tool to estimate the magnetic flux and help to define other information. So I show you the dimming and the flare ribbons for the first flare, C flare in this event, and for onset, impulsive phase and the decay of the second flare, M flare. And you can see firstly, we have some dimming regions. Mostly we have here flare ribbons. Then we have dimming region without flare ribbons, then together. And flare ribbons are really small dark parts here. And the last one. Both dimmings and ribbons flux rates are the same order. We see, also I show you another plot, contemporary peaks in the growth rate of this evolution. On this plot, we show the flare flux from Solar Orbiter STIX instrument and from GOES instrument. You can see the enhanced flux for the C flare, firstly very rapid, and then more diffuse and stronger flux for M flares. Then we have flare ribbon flux. The first also a lot signature, and then more diffused with 2 peaks. And the dimming flux with no response actually for C flare. We don't see the dimming here, but we have the strongest response for the M flare. And we can see for some time only dimming region had response, but in flare ribbons we didn't have. That could mean that the magnetic reconnection could be located upper in the layers and didn't make any signatures in the lower in the photosphere. So in this plot, I showed you the flux rate with solid line and cumulative flux with a dashed line. So both dimmings and flare ribbons can allow us to estimate the flux during magnetic reconnection for the event. And together they can be a good diagnostic tool for this estimation. That's another potential of using the research on the dimmings. And the last interesting question that we want to answer here is relation to direction of coronal mass ejection, another very important key parameter for the modeling. Usually dimmings are used as indicators of events on front side of the solar disk. If you have a halo event, it's impossible with coronagraphs to understand is it Earth directed or not. But usually scientists check the solar disk if we have here dimmings or not. But when we study a lot of dimmings, we can see that they not only indicate the event, the onset of event, but they also show very different morphology and evolution. And our hypothesis here is that this morphology can be related actually with the direction of the event, reflects this direction on the solar disk. Here you can see again September 6th event in coronagraphs. It's halo event, and the brightest part goes to the northwest. And we can see the dimmings in the solar corona, and we also can see the northwest direction. In some studies, people already tried to relate dimmings and direction of coronal mass ejection, but they couldn't make it qualitatively. So they just mentioned that dimming can indicate some propagation, or asymmetrical dimming evolution indicates that the event is not radial, that imprint is not around the eruption. But we want to compare them. And I will show our method on the case study of 28 October 2021 event. This is also halo event with a bright structure coming into this site. You can see coronagraphs images, goes SUVI images in UV. You can see here dimming, the filament also eruption, and the UV wave around the sun. And in base difference images, nicely, we can see the coronal dimmings, which we will detect. This event is also associated with X1 flare, very strong event. And we use our framework to define the dimming region. We detect it here. We use base difference data to also detect the parts distant from the eruption. We define this sector system on the solar surface to define the direction. We make a polar coordinate system with a pole in the eruption center, and we define sectors around the whole solar surface. Here we have 16 sectors, but we can define this number manually. And we also introduce area correction. As I already told, we define the dimming on the solar surface, and we need to accurately estimate the area in each sector. For that, we need to consider also different weight of each pixel into the area contribution. And we calculate the area of each pixel using double integral on the solar surface, which we compute analytically and then using rectangle method computationally. And we define for each event so-called area calibration map, which shows a ratio of area of each pixel to the pixel in the center of the sun. And it can be used for every image of the event. So we can construct this area for any radius of the sun for any image. And actually, this method can be used not only for the sun, but for any surface that we're interested to study. And you can see how this correction actually influences our results. We want to define the area of the dimming in each sector to define this the dominant direction of the dimming propagation. If we just consider square pixels, this is black dashed line, and this is an area in each sector. But if you consider the weight of each pixel, it's really differs. Our results show that the dominant direction, the dominant sector of the dimming is sector number 14, in this direction. We can save this information. Next, to compare the dimming with propagation of the flux rope, we will use the filament as a signature of this propagation. And we perform 3D reconstruction of the filament in 3D space. We take the points on SDO data, which I mark, And we match them with identical points on stereo data, point by point, using epipolar geometry. So we reduce the uncertainty for this task from 3D space to from 2D space to one epipolar line. Then we define these points in 3D space and calculate their orthogonal projection on the solar surface. We do it to compare the propagation of filament and the coronal dimming direction in one coordinate system on the solar surface. We also derive kinematics of this filament, and you can see here height, speed, acceleration in comparison with the flux. And this filament reaches a height of 300 megameters with speed of 250 kilometers per second in 3D space calculated. So we define the orthogonal projections on, of the filament, and we show them on the solar surface. Here you can see the sectors of the dimming region, the dominant direction of the dimming by sector 14, the points of the filament reconstructed for each viewpoint as though on stereo, and the orthogonal projection. Orthogonal projections are, don't depend on our viewpoint. So we see that they're all located in sector 14, and it is true for any viewpoint we see. So it's in 3D space. So we can tell that actually coronal dimming reflects the propagation of filament. And we could compare it for the first time here. You can see also coronograph images with propagation of filament. So this is the first result. We can see that the dominant direction of the dimming reflects the filament in the low corona. But we also want to study this relation with the overall morphology of coronal mass ejection. And for that, we want to compare the results with modeling of coronal mass ejection bubble. It's usually performed by a graduated cylindrical shell model, GCS, which shows us, which fits the model of so-called croissant to the image of coronograph. This model considers that coronal mass ejection is ejected from the center of the sun. The croissant is fitted, and they also consider always the radial propagation. So this model doesn't give us the source location of the event, and it doesn't give us inclination from radial for the event. But we can compare it with our results for dimming. You can see here in 3D space, when we show the dimming and the GCS model, the dimmings nicely aligns with inner part of the bubble of coronal mass ejection. This is a very important result that we need to consider not only the dominant direction of the dimming, but the overall morphology. So this is almost radial propagation around the eruptive center, and it aligns with the inner part. We also wanted to compare it, and we made orthogonal projection of the bubble on the solar surface with this inner part, and we show them by red color on the sun. You can see that it's aligns with the dimming. GCS gives us direction in terms of longitude and latitude of the source. So the source of GCS is shown with red. It's the direction of the main axis. And usually scientists check how far it is located from the eruption source. And if it's the same coordinate with the flare, that means that the event is radial. If it's far, that means some inclination happening. And we decided that coronal dimming can also give us this information and can help to estimate actually this main axis. So if we define center mass of our dimming, if we consider the weight of each pixel and coordinate of each pixel, and define the center mass, I show it by a red point, we can see that it's not far actually from the GCS parameter. And it can also show us the inclination from the source and potentially the inclination from radial direction. So coronal dimming can also help us to validate our results for GCS. If we use not red but green point derived from center of mass, we will achieve almost the same croissant shape, which is in the uncertainty interval. So we can use center mass as additional validation measure for the axis. So dimming morphology reflects, the overall morphology reflects the inner part of semi-bubble, and the center of mass can serve as an additional validation measure for modeling. And here I show the results of this project in one picture. So we can together compare dimming, filament, and coronal mass ejection model. I can also show that blue mesh is the inner part of the semi-bubble. We have dimming contour, it's the dominant direction. And we can see this also in results, that the evolution of the dimming reflects both the direction of low-lying part and the overall morphology and propagation of semi. That means that we can use coronal dimmings to provide insight into the direction and validate our results of modeling. These results, these outcomes in our framework allowed us to create a new method to develop this idea and not only compare the relation of dimmings and coronal mass ejection in terms of direction, but also reconstruct the direction of coronal mass ejection using coronal dimmings. And I will shortly describe this approach. We create a number of cones. We use cone model to describe coronal mass ejection shape, just a simple model, which can be defined by 3 parameters: height, width, and inclination angle from radial, if you consider the same source of cones. And we make these cones and create orthogonal projection of the solar surface and check how they look and check if they align with the coronal dimming. And then we make inverse problem, inverse task. We use coronal dimming morphology to reconstruct the ensemble of cones from it. Our previous results, sector analysis and dominant direction, give us this the source point, point C, and the edge of the dimming along the dominant direction, point E. Using these 2 points and prolong them from the center of the sun, we can create an ensemble of cones which will have the same source, and all the heights will be projected to the dimming region, to the edge of the dimming. And all these 3 parameters will vary in this ensemble of cones. And we can define by some empirical metrics what is the best alignment. And for this event, we define it as this number of parameters, how the cone aligns with dimming. And we also validated our result with another, with GCS model for this event. And we compared the dimming, the cone and the GCS model at the same time. And we can see that the main axis of GCS, this is blue, and the main axis of our cone actually show us almost the same direction. If we calculate the angle between them, it's almost only 6 degrees. And also another interesting outcome is if we compare for the same time, we have our cone and GCS bubble at 6, I think at 6 radius of the sun. And we can see that this cone aligns with the inner part, even with height of this bubble, which also confirms our previous result. And it's a very interesting outcome. Thus, coronal dimming can be used as the early indicators of coronal mass ejection direction on the very early stages before we can even detect them with coronographs. This was the last method that I wanted to introduce to you. And now we can sum up all our discoveries. In this project, we defined and developed a comprehensive framework for the dimming analysis, including pre-processing results to advanced method for dimming analysis. We provided the first comprehensive multi-viewpoint analysis of coronal dimming and coronal mass ejection and associated the parameters coronal dimmings to mass and speed of coronal mass ejection. And we confirmed this relation for off-limb viewpoint. We demonstrated the dimmings in general, how fast they recover, what are the trends of recovery, and that some parts of the dimming cannot recover in 3 days. And also the total dimming region shows 2-step recovery which are interesting outcomes. It also shows that dimming propagation and the dimming morphology can reflect the direction of coronal mass ejection. And we validated it with modeling results of the events. To answer all our questions which we performed in the beginning, coronal dimmings offer unique potential and high value for early diagnostics of coronal mass ejection. And they give us information of their mass, speed, the replenishment process of the corona after eruption, or the magnetic flux released during the eruption, also determination of the early propagation and estimation if the event can be geoeffective or not on the very early stage of the evolution. Thank you. That was all. Thank you.
Thank you very much, Galina. So this concludes, yes, your presentation. And now we may turn to the Q&A session. And for this question and answers, we'll start with the jury members online. So please, Dr. Vladimir Kalegaev, have you questions for our candidate today, remarks, comments?
First of all, I would like to say that this is very interesting and very actual work, and the report was enough good and impressive. I would like to say that in this talk we see very good results, and me as the person who interested mostly in the magnetosphere, for me it is interesting how to is it possible to implement the developed methods for operational needs. Does it possible to use the software created in the Space Weather Center, some Space Weather Center, to allow predict coronal mass injection input to the Earth environment to predict geomagnetic storm in automatic regime?
Thank you, Vladimir. Actually, yes, we are working on automatic software. Our colleague Shantanu Jain will, I hope, do this project. And the idea is to make it, all that I described about the determination of the direction can be done automatically, just having a dimming map. And this map can be done already in, I don't know, 2 hours after the event. And all the cones and all the direction can be done automatically without looking by eyes. And these parameters can give us already direction in 3D, which we can use to later modeling results as an input.
Did you try it already without the influence of the developer of the program? I think the main problem is to automatically find dimming corresponding to the flare. So do you have some experience in such task already?
You mean if you can detect dimming in real time and use? Or?
Yes, yes.
We checked also. Now it's only available, as I know, solar dimming results for the dimmings, but they don't allow us to make it accurate. So the detection should be done more precisely for this result. And the detection of dimming, it's actually really important here to define this dominant direction and then define the cone. That's why in real time, it's for now, with methods that are in public, it's hard to do. So it's impossible, I think, with solar dimming. So we need to think about fast detection of dimmings. Thank you.
Thank you.
So, Dr. Kalegaev, no more questions?
No more questions.
Okay, good. So I have a question for you. Are you satisfied or not with the changes done to the thesis after your report, your comments?
Yes, yes,
So
I'm completely satisfied.
Okay, thank you very much. Thank you very much. So next, Dr. Anatoly Petrukovich, do you have questions, remarks?
Yes.
Yes,
First
please.
of all, thanks a lot for the detailed presentation. I have a question related to the statistical uncertainties of your results. What do you think? What is the main source of errors in your forecasts, in your identification of images and of properties of dimming? So finally, you should finish with the properties of coronal mass ejection to be practically useful, so to speak. But you start with some images on the sun. So what do you see as the main source of uncertainty in the final forecast in your method?
Thank you for the question. Yes, of course, one of the main uncertainties is detection of dimming in our method. And for statistical analysis, we also show the uncertainty in our evolution. So we use our thresholding method and we change our level of thresholding and derive the same parameters and show it. It's also for sure important for time recovery analysis to define the dimming mask. For direction also, I think it's main source of uncertainty. So the detection of the dimming, which we also show how we evaluate this uncertainty. For the coronal mass ejection, in that data set, it was good that these halo events, which were seen from Earth-Sun line, were also seen from stereo. That's why the level of uncertainty was less. So there was good view to compute coronal mass ejection mass and speed in projection. Yeah. So I think it's detection of the dimmings, and we also show which level of uncertainty is here.
Okay, thank you.
Thank you.
So you have no other questions of remarks?
Yes.
No? Yes?
I have no other questions, yes.
Okay. So please, can you confirm whether or not you are satisfied with the changes introduced to the thesis after your remarks in your report?
Yes, I am satisfied.
Right. Thank you very much. Thank you. We now turn to Dr. Hugh Hudson.
He's trying to unmute himself. Thank you very much. That was a wonderful overview of a very comprehensive and good thesis, I think. I do have a couple of questions. One question follows up on what Professor Petrukovich brought up from the statistics point of view, but rather about the physics of the indications you get about the CME direction. So I think it's important to recognize that the medium in which the CME is propagating is initially is low plasma beta, according to the observations. And so therefore the main the Lorentz force is the main determinant of how things move. Whereas on the other hand, the observations don't show you the magnetic field, they just show you the mass that's being moved around. And so the question is, in these discrepancies that you discussed between the directivity method in chapter 7 and the filament motion, is the filament would be physically quite distinct from the CME plasma because it's cold and not hot, and it may have a different plasma beta. So is there any suggestion that you can see that happening in your comparisons, namely the difference between the filament motion and the CME motion in terms of the Lorentz force that's applied from the pre-event structure? very complicated question, I know.
Thank you, Hugh. I just didn't hear you very clearly. Maybe can you make a shorter version? I just
Okay. Short question is, can you infer something about the Lorentz force that might cause the source of the Lorentz force that might cause a discrepancy between the filament motion and the dimming, the direction that the dimming infers?
Yes, you mean the case study of October event, which I showed for direction.
Yeah.
And we obtained really different direction from filament and from GCS.
Yeah, so basically I'm asking why is that? That's the question.
And actually, yeah, it mostly corresponds not to the main axis, but maybe to the, what's called, to leg or part of the coronal mass ejection. And also, if we go clearly in the observations, we saw the other part erupting, small part of the filament. So actually, this filament had like a double structure, but we could resolve only this leg. And that is also a question if we can use filament for to derive the direction of coronal mass ejection. So we also need to consider the complex structure, but we could resolve only this part. And that means also that in the early phase, the filament drove the dimming direction also.
Oh, that's interesting.
This part. And that's why maybe we can see this dominant direction here, but the overall, it's also another. So maybe on the early evolution, it drove also with filament, which is low in the corona and closer. Yeah, this difference between these parts was really confusing for me when I did this event.
Okay, but I think it's confusing, but it's also interesting and needs to be explained. So I have another tricky question for you. Thank you for that response. So the other tricky question is about the use of the LBR, the log base difference, LBD, LBR, the logarithmic base difference visualization. I understand that it really works well and it shows you much better what's happening, but I've always had trouble with this because it's the logarithm of the ratio as opposed to the logarithm of the difference. And so the logarithm of the ratio always will have information about the background structure, which is not what you want to see. You want really just to see the event itself. So the general question is, this is a systematic bias in the log base difference representation. Does that affect anything? Do you think that has any effect on your conclusions?
Thank you for this question. Yes, I think it's the most significant. It can be for the recovery when we track the dimmings for several days. And that's why we also try to come up with the methods which can show us the original intensity. So for example, in area box, I show both ratio and the original intensity to see what we actually track.
Right.
Yes, somehow, at least here, it can be solved like this. Of course, when we detect dimming, we need to always manually check what is detected. And for example, also this October event, usually I detect dimming in logarithmic base ratio, but here also was a filament eruption in the same, also distant part of the dimmings. So for example, I needed to switch to absolute change for the base ratio, which also gives us uncertainty. But at least all of this, we need manual decision to come up what we detect actually and what is here. When I studied in sector analysis, it was also hard that maybe it's just the coronal loop of layer at the same time was at the same place, and then in ratio we have this uncertainty. And that's why we always need to check thoughtfully. When we also come up with a fixed mass approach, which shows us the total region of the dimming, firstly we use cumulative dimming. But then we saw that a lot of flare parts are in the same region. And we decided to go with instantaneous to not to include some parts. So it's also somehow helped us to minimize uncertainty here. But yes, in complexity with also differential rotation, logarithm-based ratio gives us uncertainty. But still, for checking impulsive phase of the dimming, it works. This analysis works nicely in this approach.
Okay,
So we need to always be careful. Thank you.
That's the answer is yes, you must be careful and look at the name. So thank you very much.
You need to understand what we're detecting.
I don't have any further questions.
Thank you very much, Dr. Hudson. I have a question for you. Are you satisfied with the changes made to the thesis after your remarks in your report?
Yes.
Right. Thank you very much.
Thank you.
Our next jury member, Dr. Stefan Hofmeister.
Yeah, thank you for this great presentation. I think it was a really strong and interesting presentation. My question, my first one, would be about the channels you have chosen of the satellites. I've seen that in the earlier studies, the 211 channel of AIA was used, but that you used the 195 channel of stereo A and B, if I have seen that right. What is the reason for that? So how do the different channels differ in the dimmings which you see, and why did you choose the channels you used?
Thank you, Stefan, for this question. So according to studies which check dimmings in multiple wavelengths, the dimming mostly the best way detected in 2011, 171 and 193. So it's quite some temperatures, about 1 to million Kelvin. And so we need to detect dimmings in these channels, which also gives us different information and different height of the layers. And for the off limb, we used 195 as it had, so it's also in the list, and it also had good cadence for this time period. So it was just also good data and proper channel. For SDO, usually we detect in 2011, but also in for case studies, sometimes the dimmings better is seen in 193. That's why.
Okay. So the dimmings basically, no, the channels, they basically probe the temperature of the corona at different heights, or at slightly different heights. If you look at the dimmings in the different heights, so in the different channels, can you get additional information out of that? So a better estimate on the direction of the CMEs or something like that?
That's an interesting question. For direction, it's hard to maybe estimate now because we also have this sector analysis, which gives us uncertainty of the direction. So anyway, I think dimming indicates more or less the same propagation, but here will be maybe just small change within these three channels. For example, I think for magnetic flux, it can give us different result because if the flare and magnetic reconnection happens in different layers of the corona, maybe it can give slightly different, I think, values. For area and brightness, I think more or less. In this work by Karen Desauer, they show for on-disk dimmings, different channels and how the dimmings are shown. And we can see that for these channels that we use, more or less good indication of dimmings. But yes, we can always check in different.
All right, so a very short last question. If you could wish for an instrument or different satellites and satellite combinations, what would you like to have for CME forecasts for the combination of CME reconstructions from coronagraphs and your dimming analysis? What would be the best combination what you could wish for?
Very nice question. Of course, I wish for L5 mission from master I was really interested in this position, and which gives us also 3D vision. Of course, we need always to have several positions of satellites and good UV imagers, really with good resolution to detect our dimmings and other stuff. So I think L5 position will be my best candidate. But also I think it's really interesting what nowadays we have this Parker Solar Probe and Solar Orbiter, which gives us unprecedented information, and we still will dive into it. But yeah, I'm really waiting for L5 visual mission. Thank you.
Right, thank you.
Thank you very much, Dr. Hofmeister. Are you now, I mean, I have this question for you, obviously. Are you satisfied with the changes introduced to the thesis after your review?
Yes, I'm satisfied.
Right. Thank you very much. Now we may turn to the internal jury members, and I will start with my colleague, Professor Clément Fortin.
Yes, thank you very much. Thank you very much for the presentation, Galina. Of course, my interest has to do with the operational aspects also on aviation flights at high altitude and for astronauts, and how long would it take for a system? You mentioned Jane's work, but how long will it take before we have a prediction system that can prevent what happened to SpaceX, or what happened that the crews would be protected at some point? I know protection against radiation is extremely hard, but you're at least with the calculations that you aim to get, when do you think we could get some more reliable or very reliable predictions for helping air crews and astronauts to be more protected?
Thank you for this question. So we're studying coronal mass ejection, and these clouds arrive to Earth from 1 to 3 days. For very fast events, it can be 1 day. Usually it's 2-3 days. And we have this time already to think. And we see the eruption of coronal mass ejection on the sun. So we have this 3 days in advance. And if we use, I hope, coronal dimmings, and as we want to do before even we detect them from coronagraphs, we can obtain, I think with dimming, we can, in the first hours of the evolution, we can already define this direction and define the parameters. And so we already have it in the first part of the day. And we have still 1-2 days to, like in ideal, of course, only relying on the dimmings. And of course, it's also all probability. And even with modeling from sun to Earth, sometimes the event doesn't reach Earth and doesn't give impact. So it's all probability. And the question if, yes, people rely on this forecast or not, as with SpaceX, for example. Yeah, but yeah, ideally with dimmings and nothing happened after on the way from the sun to Earth, we can say it very fast.
So you can predict very fast
if you consider only the dimmings and what we discuss here, and don't evolve other, for example, if there are 2 events, they can interact and there will be other, it can be deflection of the direction or the speed. It can be faster or slower, and also solar wind and coronal holes. If you just consider the dimmings, so then it's the first hours of the evolution, and then we have these 2 days to arrive for the event, for the coronal mass ejection. So it's fast.
Okay. Thank you very much. So there's a lot more work to be done to be successful in this area. Yes. Thank you.
Question, are you satisfied with the changes?
Yes, I am.
Thank you very much. So, my turn. So I had the pleasure to listen to you at the thesis final review, and we discussed some physics aspect already. Here, in your presentation, which was quite thorough, I missed something, which is, let's say, related more to the methodology, in the sense that you see on slide 7, you list your research objectives and questions and gaps. However, what I miss somehow is the explicit expression of the hypothesis, because you create this great framework and it appears like, okay, you were so inspired. Of course, you have a nice collaboration, great supervisor, great team, great collaborators. But the hypothesis that led you to build up this framework. So if I would say like this, what was, let's say, your main hypothesis? What led you to think, okay, I can do this framework that way and not that way?
Thank you for this question. Yes, as there was 3 different studies, I had like really different hypotheses for each of them, and then I needed to combine them into one, and that's why it was hard to make, like, estimate just one hypothesis and not to repeat, you know, other parameters of methodology like novelty and aims. And in my opinion, the hypothesis is that nowadays dimmings are mostly used as indicators, just indicators of eruptions, but we can make this work important for forecasting and operation, so we can estimate the parameters of coronal mass ejections from dimmings. And that led us to other questions. Which parameters and how can we do it? So the hypothesis is that dimmings can be used to estimation of the parameters of coronal mass ejection, not only indications.
Right. Okay, thank you. In slide 30, you speak about these sectors, you see, for the question concerning directivity. So you split the sphere into 16 sectors. So the naive question from my part is, and you said this, we could divide in any number of sectors. So why 16? I mean, did you try like 12 or 24 or 30? And if you did, what were the difficulties associated to that? And why 16 maybe as some sort of optimal number, or the number that facilitates the analysis?
Yes, thank you. This is a very good question. So when we developed this method, the first idea was to make it fully automatic and make dimming direction automatic. And just we define the same sector system on the sun, let's say 12 or 16. And we make the same system for every event, and it will work great. So we just put the map of the dimming and define, but that actually didn't work in my case and in case of this event. And
excuse me, when you say it didn't work, what was the outcome that led you to think, okay, also, this does not work?
It's also give us bias, how the size of the sectors and the dimming region. So if the dimming region located on the edge of the sector or in the beginning, we already have the uncertainty like one sector, and it can be a lot. And that's why we need to come up with good number of sectors and location. So how we define them from the north, and then we can maybe rotate it. And for now, the best way, and now we use this sector system also for the method, the last method to define direction. And here the idea actually is use the same, always the same sectors. And now we use 12 sectors from the north. But while we develop the study, I also feel that we need rotate. So we always need to check the dimming and then rotate the sectors. So always 12, but rotate the sectors to have the edges and the edges of dimming and sector at the same time to eliminate this bias. But yeah, so the best way will be do like this. But we will make more statistics, and if we will see if it can work with the same system or we need always rotation.
Okay, thank you. So that will be all for me today. Thank you very much, Galina. And of course, I can state that I'm satisfied with the corrections and let's say the changes in the thesis. Thank you very much. So I see that we have guests also in Zoom with us. So dear guests in the audience, if you have scientific questions related to the thesis or remarks to share with our candidate, please. Maybe Astrid, Veronique, yes, hello.
Yeah, hello. Yeah, maybe just a short comment. So I think it was a very presentation, and I think the work has shown, he has introduced a number of new interesting findings and coronal dimmings in associating with CME. So just to congratulate you to this work.
Thank you.
Thank you.
We have also Karin this hour with us. Hello.
Hello. Yeah, I would like to also thank Galina very much for this very nice presentation, and also congratulate her to this really nice thesis work. And I have probably one question related to the orthogonal projection that you mentioned that is used to determine the direction of the CME. Could you maybe explain a bit in more detail why the orthogonal projection was used? Like, what was the motivation to use specifically the orthogonal projection for the dimming project?
Thank you, Karen. The orthogonal projection can be really reliable indicator to make a comparison of the direction for us, because they don't depend on the viewpoint. So the projection on the surface will be always at the same point on the sun in 3D space. For example, line of sight projection always depends on the viewpoint and what we can see by the satellites, what we see in images of the filaments. For example, coronal mass ejections, they're always line of sight for us, and we don't know the actual location in 3D space. While orthogonal projection will give us the estimation in one coordinate system. And we even for 28 October, we show the difference of line of sight projection and orthogonal projection. And for example, if you use line of sight projection, so it will be different sector with the dimming, not the same sector. So, but it depends which we use, SDO we use, or we use stereo, while for orthogonal projection, it doesn't matter.
Thank you very much.
Thank you.
Thank you. Any other question from the audience with us on Zoom? Seems not. So here in this room, do we have questions or remarks? No. Okay, thank you. So it is time to have the word of the supervisor, please.
Okay, in my opinion, this is an excellent and very interesting work, and the main outcome that it gives some light to the solar physics community, that coronal dimmings can be very great indicators for early diagnosis and evolution of coronal mass ejection. And another important outcome, I think, that framework that was developed gives the path to many new studies. And we already started a very important study with another PhD student, Shantanu Jain. And I just want to thank Galina for this great and beautiful work.
Thank you, Tatiana and Shantanu.
Thank you very much, Tatiana. So now it is time for a closed deliberation. So please You may. And for the, we need to have the breakout room.
Yes.
Thank
so,
you.
Okay, let us. Ksenia, may I also ask you to leave?
So, Galina, welcome back. So, on behalf of the jury, all the members, I'm pleased to announce that we accept your thesis as is and that we award you we recommend the award of the PhD degree.
Thank you so much. Very, very happy. Thank you so much for being with me today. This year was really challenging, but I'm very, very happy to spend this year in Caltech and to be a part of this, of his history and to be a part of this university. I'm very thankful to my supervisor, Tatiana, who introduced me to this field of space weather and always inspired me and gave me brave ideas, and together we were really creative. I'm thankful to Karen Dizauer and Astrid Veronik, members of my doctoral committee, and who also supported me all my way from master to PhD. And I'm really lucky to meet you so early in my scientific career and to work with such professionals in this field. I'm very thankful to Shantanu Jain and Julia, who were part of this research and who contributed greatly to this work. And we will develop it further. And I'm very thankful to my doctoral committee, to my defense jury members. Thank you for being with me today, for your time, and very appreciation of my work. And it's an honor to have all of you in my jury this day. And of course, thank you to my family and friends for all these years and support. Thank you so much. I'm very, very happy today. Thank you.
Thank you, Galina, and congratulations.